Okay, kids. Today we're getting into Unit 5, and Unit 5 starts with a lot of review, so that might be good, but probably not good news for a lot of you because I don't know how many of you actually really understood what was going on with dimensional analysis in Unit 1, and we're just getting right back into dimensional analysis with mole conversions again. So go back to Unit 1 and make sure you understand those mole conversions. We're going to review them, but that's the kind of the initial part of Unit 5 is we're doing mole calculations, mole conversions, and stuff like that, but we're going to be adding a couple new measurements that we're going to use with our mole calculations. So make sure you go back and review our dimensional analysis lessons, and we'll be doing it in class, but again, dimensional analysis is going to be a big part of the course moving forward from this point. So that's why we introduced it in Unit 1 and we're coming back to it now. And the better you understand it, the better off you're going to be when it comes to using measurements like molarity, which we're going to get into today. So today's lesson is how do we use molarity? What is the measurement of molarity and how do we use it in dimensional analysis, and how do we calculate molarity, and then how do we use it in dimensional analysis? Okay, so that's what today's lesson is going to focus on. But before you watch this video, I would strongly go back, and I strongly urge you to go back and review your mole map, just what dimensional analysis is, and make sure you remember what Avogadro's number is, how to calculate molar mass and all that stuff, because it will come in handy. All right, so let's get into it. So again, let's look at Unit 5. If we look at the VLOs in Unit 5, notice that we have a lot of mole calculations, grams to moles, particles to moles, moles to particles, okay? But notice there's a few other calculations in there that we haven't talked about, so we're adding to our kind of mole map and our mole conversions calculation, okay? So if we look at this mole map pretty much has everything we're going to add to what we already know. So we should look at this mole map here, and as we go across, we should be understanding how to go from grams to moles, moles to particles, or particles to moles, moles to particles, or moles to grams. We should understand kind of this part of the mole map, okay, the horizontal. But we're going to learn these two parts as we start Unit 5. Okay, so this lesson is about molarity. Okay, and notice it tells us if we look at our mole map, we can use molarity as a conversion to go from volume of a solution in liters to moles of our solute, or moles of solute to volume of solution. Okay. All right. So let's talk about what molarity is, and let's make sure we understand what a solution is. Okay. All right. So also you might want to check out these handouts. It kind of reviews the basic things we're going to learn today on molarity. All right. So here we go. All right. So molarity is a measurement of concentration. When you see capital M, you need to think molarity, or if you see these units, moles per liter, you want to think molarity. So molarity is capital M is moles per liter, all right? Now it's a measurement of concentration. So first off, we have to have a solution. And normally we're talking about an aqueous solution. So we're talking about stuff dissolved in water, right? We made a solution. We took a salt or a sugar or some kind of compound, and it mixed with water and it made a solution. Remember, a solution is just a homogeneous mixture, and water is the solvent. Okay, so that's most of the time what we're going to be talking about. Okay, and molarity is a measurement of how concentrated our solution is. So what is a solution? It's got a solute and a solvent. Most of the time we're talking about aqueous solutions, so our solvent is water and our solute is something else. Maybe a salt, maybe an acid, whatever. It could be whatever. Whatever mixes well with water could be the solute. Okay, and so when we have solutions, right, if I have a salt solution or an acid solution, the main question should be, well, how concentrated is it, right? Concentration is just a measurement of how much solute do you have in there, okay? I have an acid solution, but is it dilute? Do I just have a little bit of acid in that water-based solution? Or do I have a lot of acid in that water-based solution? That's an important question, right? And so concentration is just a measurement of how much stuff you have dissolved in an amount of stuff, right? So it's how much stuff you have dissolved. How much solute do you have dissolved? That's the measurement of concentration. So that's all concentration is a measurement of, all right? So if I have a saltwater solution, remember AQ just means aqueous, so I got sodium chloride dissolved in water. How much sodium chloride is dissolved in a given amount of solvent, or how much sodium chloride is dissolved in a given amount of the entire solution? Okay, both of those would be measurements of concentration, all right? And then, kind of just some vocab. If I say the solution's concentrated, what does that mean? It usually means I got a lot of stuff dissolved in it. And if I say the solution's dilute, that's kind of a way of saying I don't have that much. So if I have a concentrated salt solution, I got a high concentration. I got a lot of salt in a given amount of solution. But if I have a dilute solution of salt, then salt water, then maybe I don't have that much dissolved, right? But all concentration is a measurement of how much of that stuff, how much of that solute do you have dissolved, okay? And you could do it per amount of the solvent, like water, or you could do it per amount of the entire solution. So basically, how much of this do you have in a volume of that entire solution? Remember, a solution would be a combined salt and water, okay, in this example. All right. So a measurement of concentration is going to look a lot like density, right? Amount per amount, right? Density is mass per volume. So amount in terms of how much mass there is, and amount in terms of how much volume there is, right? That's density. And it could be a measurement of concentration, right? You could have a concentration that's grams per milliliters. What would that mean? It would be like how many grams of the salt are there per milliliter of the solution. So if I have, if I was told my concentration was 5 grams per milliliter, that means I have 5 grams of salt for every milliliter of solution, right? So that could be a measurement of concentration, okay? But what we're gonna talk about is a specific measurement of concentration, okay? It's kind of our measurement in chemistry for how concentrated something is. Okay, again, you could make up your own measurement of concentration. It's amount of this per amount of that, right? That's what concentration is. But our measurement is going to be molarity. Okay, so molarity is a measurement of concentration. It's a specific measurement of concentration. Okay, so what molarity is a measurement of the moles of solute per liter of solution. Molarity, capital M, equals moles per liter. Moles of solute, so if we have a salt solution, it would be moles of the salt per liter volume of solution, and the volume has to be in liters. Okay, that's what molarity is. So let's say you were told that you have a 1.5 molar solution of NaCl. First of all, understand that word molar is just short for molarity. So they're telling you you have a solution of sodium chloride, and that's the molarity, 1.5 molar. So another way to be given that same measurement is you could say 1.5 capital M. That capital M means molarity of a sodium chloride aqueous solution, right? So just in this little kind of statement there, I know that's my solute and my solvent is water because it's aqueous, right? And most of the time our solvent's going to be water, but there could be, if you have something dissolved in benzene, you could get the molarity of whatever solutes dissolved in benzene if you wanted to. But in this case, it's water is our solvent. So here's how we should interpret this measurement. Anytime you see capital M, you should go back to this. It's moles per liter, right? Or go back to the top of the screen. It's moles per liter. That's really how you should look at capital M. When you see capital M, you want to think moles over liters, because this is the way we're going to interpret this measurement. What does this mean right here? It means this, and it means this. It's the same thing. And notice it's a conversion factor. Okay, I can say 1.5 moles of NaCl for every 1 liter of solution, Or I could say 1 liter of solution for every 1.5 moles of NaCl. And I'm going to be using this to convert liters, to cancel out liters and get to moles. And I'm going to be using this to cancel out moles and to get to liters. Okay. If we go back to the mole map that I showed you, the original, right? Here's moles and here's liters of solution. And if I follow the arrow, what does it tell me to do? It tells me liters over moles, which would be 1 over molarity. Okay, but if we go back this way, solution, volume of the solution to moles, it tells us to use this, moles over liters. All this is our molarity measurement used as a conversion factor. Again, we could say X moles of solute per liter of solution, or 1 liter of solution per X moles of solvent, okay? So when I see this, I get 2 conversion factors, just like we did with density back in Unit 1, if you remember, okay? So understand, if you're given the measurement of molarity, you're going to use that as conversion factor to convert either from moles of solute to liters of solution, or liters of solution to moles of solute. Okay, so let's do a practice problem. How many moles of sodium chloride are found in a 15-liter solution that has a 0.75 molarity? Okay, 15 liters of a 0.75 molar solution. Okay, so again, I see that and I know this. Now you could also flip this. You could say 1 liter over 0.75 moles. But for this question, this is how I want to interpret my molarity measurement, because this conversion factor is going to cancel out liters and get me to moles. And that's what I want. I want to know how many moles, and I'm given liters. So I got to cancel out liters and get to moles, right? So what I'm going to do is take my 15 liters of solution, multiply by the molarity, which is really that many moles per 1 liter. Liters cancel out, and that gives me moles. Round to 2 sig figs because my molarity only had 2 sig figs. All right. All right. But what if we wanted to go the other way? So let's say a student requires 17 moles of sodium chloride, and they have a 0.75 molar solution of sodium chloride available to them. So the question is, how much, what volume of this solution am I going to need to get 17 moles? So now I'm going to take my 0.75 molar and I'm going to interpret it as 1 liter per 0.75 moles of the solute, because I need to cancel out moles of solute. I have 17 moles of the solute, sodium chloride in this case, and I want to get liters of solution. So I'm just going to flip that ratio, okay? And I would take my 17 moles of sodium chloride and I would divide by the molarity, which is really canceling out moles, and I'm left with liters. So to get 17 moles of sodium chloride, I would need to measure out around 23 liters of my solution, because that's the concentration of my solution. So I need 23 liters of the solution that has this concentration to get that many moles of sodium chloride. Okay. So again, what we're just going over there is how do we use the measurement of molarity in a calculation? And again, if you look at your mole map, molarity, if you know it, is your conversion from liters of solution to moles of solute, or moles of solute to liters of aqueous solution. Okay? All right. But let's understand how we calculate molarity. Sometimes you're just going to have to, be given information and then calculate the concentration. And anytime I want you to calculate the concentration, it's the molarity. I want you to calculate the molarity of the solution. So if you want to calculate molarity, remember, molarity is just moles over liters. So you could use the equation, just like density is mass over volume. Okay, molarity is moles over liters. Now it's specific. It's moles of solute per liter of solution. So in order to calculate molarity, you need to know how many moles of solute you have, and you need to know what the volume of solution is, that many moles of solute are dissolved, all right? So what if we were given this? 18.9 grams of sodium chloride are dissolved in 500 milliliters of solution. Well, I know my volume of solution, but notice it's not liters, it's milliliters. And I know the amount of solute, NaCl in this case, but it's not moles. So we just got to do some conversions, right? So molarity is moles over liters. Okay, so I should be able to take my 500 milliliters and quickly convert it to liters, right? Move the decimal place 3 times, divide by 1,000, right? So 500 milliliters is 0.5 liters, so that's what I would plug in here. But I can't plug in 18.9 grams there. I got to plug in moles, right? That's what molarity is. It's not grams per liter, it's moles per liter. I have my liters, 0.5. I just need my moles. So remember, how do we convert grams to moles? We divide by the molar mass, right? Use your mole map if you need to, but we'd have to go to our periodic table and calculate the molar mass of sodium chloride here. Sodium is 22.99 and 1 chloride is 35.45. So if we add that, we get our molar mass of the compound, 58.44. But remember, what molar mass is that many grams per 1 mole, or 1 mole per that many grams. We're going to use this, okay, we're going to divide by our molar mass to get moles. So if I take my grams and I divide by my molar mass, grams cancel out, that gives me moles. So now I have my volume in liters, plug that in. I got my moles, I got my amount of solute in moles, so I'll plug that in, right? So molarity is moles over liters, plug those in, and I get my molarity, right? And again, I need units when I express a measurement, and molarity is either capital M, or I think a better way to express it is moles per liter, okay? So you could say that as your answer, or you could say that as your answer, but this is the best way to interpret it, because now I'm gonna look at that and say, hey, I can make a conversion factor. I can say that many moles per 1 liter, or 1 liter per that many moles, right? All right. So what's the dimensional analysis way to answer this same question, okay? So a lot of times kids just like to say, okay, well, I know the equation, molarity equals moles over liters, all right? So figure out moles, plug it in, figure out liters, plug it in, get my molarity. And that's perfectly fine, but there's a smoother way if you really understand dimensional analysis, and you interpret you know that molarity, capital M, is really this. Moles on top, liters on the bottom. So the dimensional analysis way to answer that same question is, right, we did dimensional analysis to get our moles. So we would take our grams of NaCl, we divided by the molar mass, that gives us our moles of NaCl, all right? But then to get molarity, it's just divide by the volume in liters. And the volume in liters is 0.5. So all I have to do is now just divide by 0.5 liters. So extend my T-chart. And now grams cancel out. I have moles on top, I have liters on the bottom. That's moles per liter. And mathematically, it's the same thing. 18.9 divided by the molar mass divided by 0.5. And that's what we did in the original problem. All right, we get the same answer. All right. So now I kind of want to focus more on salt solutions. Okay, so ionic compounds dissolved in water, all right, and understand what the molarity gives us, okay? If I'm given a molarity of a salt, of an ionic compound, I'm really given 3 different measurements, okay? So let me show you what I'm talking about, all right? So I'm told that I have 1.5 molar sodium chloride. So 1.5 molarity sodium chloride, right? So the first way to interpret it is straight up the way we've done. So what does that mean? It means 1.5 moles of sodium chloride for every 1 liter. But we really should understand what an aqueous salt is. An aqueous salt is that salt has dissolved in water. And what that really means is those ions have separated. So this represents 1 formula unit of sodium chloride, right? And for every 1 formula unit of sodium chloride, there's 1 sodium and 1 chloride. And I can see that when I write the equation of it dissolving in water, I get 1 sodium ion and I get 1 chloride ion. So these are all 1-to-1 ratios, right? So given that measurement, another way to interpret it is to say, well, you have 1.5 moles of just sodium ions for every 1 liter, or you have 1.5 moles of chloride ions per every 1 liter, right? So just given this, you know those 3 different measurements, okay? Now, in this case, they're all the same number, okay? So again, let's think about it. I was given this, right, 1.5 molar sodium chloride, but what that really means is I know all this. And this bracket notation just means, when I have something in brackets, it means the molarity of it. So the molarity of sodium chloride is 1.5, but the molarity of sodium ions is also 1.5, and the molarity of chloride ions is 1.5. Okay, so I was just given this, but I should understand I need to interpret it that way. Okay, so let me show you another example where it kind of changes a little bit. So what if you had a 1.5 molar solution of aluminum chloride? So the reason why this is going to change a little bit is the subscript for aluminum is 1 in the formula of aluminum chloride, but the subscript for chloride is 3. There's 3 chlorides for every 1 aluminum. All right, so how should we interpret this? Okay, well, now if we look at that same equation of that salt dissolving in water, I have aluminum 3 plus, one of them, but I get 3 chlorides. So for every one of these that dissolves, I do get 1 aluminum ion, but I get 3 chloride ions. So I was given the molarity of this compound, of an ionic compound in water, but that means I was also given the molarity of aluminum, and it's the same number because it's a 1-to-1 ratio. But notice the chloride concentration is 3 times that amount. So how did I get the chloride concentration? I took the concentration of aluminum chloride and I tripled it because there's 3 chlorides for every 1 aluminum chloride, right? So I was given this measurement and I know these 3 measurements. That's how I should interpret it. So I could use this measurement to go from liters of aluminum chloride solution to moles of aluminum chloride, or moles of aluminum chloride to liters of aluminum chloride solution. But if I just wanted the aluminum ions, that's what I would use. And if I wanted the chloride ions, that's what I would use. So let me give you an example, all right? Let's say you have 25 milliliters of a 1.5 molar solution of aluminum chloride, okay? And the question is, how many formula units of aluminum chloride are in the sample? Well, let's look at our mole map and review, all right? So I'm at liters of solution, right? I'm at volume of solution, and it tells me to multiply by the molarity, and then to get particles, multiply by Avogadro's number, right? Formula unit is the word molecule for an ionic compound. So it's really how many molecules of aluminum chloride do I have, but for an ionic compound, we say formula unit. So we want to know how many particles of aluminum chloride do we have, all right? So the mole map tells me if I take my liters and I multiply by molarity, that'll give me moles, and if I take my moles and multiply by Avogadro's number, that'll give me my particles, and that's what we're going to do. But let's see how that looks in dimensional analysis, all right? So first off, we weren't given liters, we were given milliliters, but hopefully you can just move the decimal place over 3 times, and boom, you got your liters, okay? So we have this many liters, 0.025 liters, times the molarity, 1.5 moles of aluminum chloride for every 1 liter, okay? And then times Avogadro's number to get formula units, right? But what if it was the same question, like it was given the same thing, but instead of how many formula units of aluminum chloride, they asked how many chloride ions are in the solution? Well, one way to think about it is we just calculated formula units, and we should understand that for every 1, if we go back here, for every 1 formula unit of this that's dissolved, there's 3 chloride ions. So really all we have to do is take our answer from this one and triple it, right? So it was 2.3 times 10 to the 22 formula units. So that's 6.9 times 10 to the 22 chloride ions, okay? But what if we didn't do this first? What if the question was how many, you were given the same information here, but instead of saying how many formula units, it just said how many chloride ions you had, okay? Well, one way to do it is to recognize, okay, well, I was given the molarity of aluminum chloride, but if I multiply that by 3, that's the molarity of just chloride. That's the moles per liter of chloride. So we would do the same thing. We would take the 0.025 liters, multiply by the molarity of just chloride, and we had to recognize that it was triple the molarity given, 4.5 moles per liter, and then times Avogadro's number, and we get our same answer, okay? Now this calculation, that interpretation is kind of a more advanced interpretation of it. That's what we're really going to focus on when we get to Unit 6 in stoichiometry. But I still think the better you understand what molarity is, and the better you understand how ionic compounds dissolve in solution, the better off you're going to be moving forward through your entire chemistry career. All right, so that's why we brought it up. But hopefully we understand the measurement of molarity, what it can tell us, what calculations we can do with it, and how we can calculate it, and what we need to do to calculate it. All right. So that's it. Hopefully you found it helpful.